Welcome back to the Causality for AI and ML lecture. This time it's me and Moritz who are in charge of the holding the lecture and providing the slides. Matej is not here today, and today it's about causal discovery. And we're gonna look on four sections here. First, we have a brief recap on structural causal models and how they relate to causal graphs. Then we're going to look at constraint-based causal discovery, just giving an intuition, an example, and the same for score-based and additive score-based causal discovery and additive noise models. So let's start with the brief recap. This definition should be somewhat familiar to you by now. So we have an SCM, which is composed of, which is defined as a tuple, U, V, and F, and P, where U is a set of exogenous variables and noise variables. V is a set of endogenous variables, so everything you aim to model in your you're interested in modeling basically. And P is a distribution over your exogenous noise. And F is a set of functions that basically define the causal structure and the mechanisms connecting your variables. You've already seen this ladder of causality, and when we ask what we can do with SCMs, probably Matej already told you about interventions and counterfactuals and so on. So we can do three things with these SCMs. The first one is the first level of this ladder is like seeing, so observing data, so observational distributions, everything you encounter when you go through the world essentially. Then you can do certain things, so you can intervene on systems, and by that you can you get an interventional distribution, and you can kind of predict what will happen if I intervene on some variable. And the counterfactual, so the imagination level of this ladder then allows you to do some kind of retrospective analysis. So you can ask the question, what would have happened if I had intervened on some variable given some certain context? So as I said, each variable, each endogenous variable in your SCM is computed by using such a function where PA is the parent set of your variable of interest, denoted by I in this case, and some additional noise. And in this lecture, we assume that an SCM is defined recursively, which simply means that we don't have any cycles in our SCM. So we don't allow for feedback loops. What does this mean for our definition? So we can go ahead and press the laser pointer, by the way. That one? No. Sorry. Back again. So you can go ahead and replace these variables here with their definition, and you can do this until you can represent your SCM just in terms of noise and such chaining of functions basically. Yeah.
The online recording in the content.
Yeah, okay, sure. So for everyone who's online in the Zoom session, we will see an example in a minute. So if you didn't get it by now, then that's not an issue. So there's the example I talked about. So in this case, we have four variables in our SCM, which are the endogenous variables, so x1 to x4. We have an exogenous variable, u1, basically defining the kind of the root or one of the roots in our SCM. And then we can go all the way down to the definition of x4. So what this means, and represented as a graph. Let's start here with this u value. This u determines x, and then x determines, so x3 then is determined by x1 and its corresponding noise. X2 is determined by x1 and x3 and so on. I think you get it. So a variable is always determined by its parents and some kind of noise. And you can then say that a certain SCM induces a directed acyclic graph, acyclicity because the SCM is recursive. And it also induces a joint distribution over all the endogenous variables as well. You've already heard about deseparation, I think. So all the deseparation properties you've seen in former lectures, they still hold here. So if you look at this example graph again, you see these the deseparation properties basically tell you these independencies. So x1 is independent of x4 given the value of x2. That which you can see in the graph right here. So if you get to know this value, there's no kind of information flow anymore between x1 and x4. Yeah, and the same can be seen for x3 and x4. So the same conditional independency holds. And however, SCMs are in a semantic way, they are have a stronger semantic than classical Bayesian networks, for instance. So in a Bayesian network, you would be allowed to turn this edge here, and this still gives you the exact same deseparation statements in the graph, and as we assume Markovianity and with several other assumptions, this also transfers to the distribution induced by this graph. And so you still have the same set of independencies here. However, with an SCM or within an SCM, if you turn this edge, this suddenly gets a meaning. Yeah, so you have a causal meaning here. X3 causes X1 in this case, and we will see in a minute that this makes a difference in the when it comes to making interventions and also counterfactuals. Oh, come on. So here we see then again the same graph. Yeah. So on the left hand side, the original one, let's say, and here is the one with the current edge. And if we apply a due calculus and intervene on x1, indicated by this pretty hammer designed by Florian Busch, then we suddenly obtain that nothing really changes. So we cut off this edge to the exogenous variable, but that's it. Yeah, semantically, x1 still has an influence on x3 and on x2. However, if you look at the right-hand side, you see that cutting off this edge changes the distribution in the sense that x1 is not dependent on x3 anymore because we set the value of x1, right? It's set, so we can choose x3 as we like. And this indeed leads to a different distribution. And so you can say an SCM has kind of a stronger semantics in that sense. So here's a different interventional distribution if you consider these two graphs, and if you swap this arrow or this edge. And one key result based on this observation is that in causal discovery, if you observe data from the distribution, as we have seen, the observational distribution is the same regardless of the orientation of the certain edge. Now it's not working again. So turning this one doesn't change the deseparation either. So it follows that also the observation distribution doesn't change, right? And purely observational data isn't enough to fully recover the causal graph, at least in general. You can make certain assumptions that still makes this possible, and we will see that. But in general, you cannot identify the full causal graph just by observing. And instead, what causal discovery algorithms typically do is they only guarantee to recover a so-called Markov equivalence class, which basically states that it guarantees you to determine all the deseparation state properties correctly, however, not more. And we will see several examples of that during this lecture. And the implication is that in the Markov equivalence class, the V structures have to be all the same for all DAGs, and the skeleton has to be the same for all DAGs. As an example, let's look at this 3-variable case here. By the way, I think I skipped some of your slides, right? Anyway, I hope it doesn't harm regarding understanding. So we have these 3 variables, yeah, x1 to x3, and on the left-hand side we have 3 candidate graphs, and these graphs essentially represent exactly the same Markov equivalence class, so they encode the same deseparation statements, and also then the distribution entails the same conditional independency. And normally you would represent this visually as an undirected edge. We have also corrected this already, but I have opened the wrong slides. In the channel, there's the corrected one. I mean, I think I just proceed. I think it doesn't really matter. So in this case, we represent this as a double arrowed edge to indicate that we allow kind of for both directions. But there's a clue. We don't allow this one. So because this is a collider, yeah, and as you remember, conditioning on a collider makes the parents dependent on each other. So this does not this graph is not entailed in this Markov equivalence class. However, in this case, this graph defines its own Markov equivalence class. So after this brief recap, you may ask, okay, cool, now I have these graphs. Let's go ahead and just use it. Well, surprise, surprise, you usually don't have it. You have to learn it somewhere, in some way, right? And why should we do that? Well, there's a very prominent example showing that statistical relationships or trusting statistical relationships only shouldn't be done all the time. So here's a graph showing the chocolate consumption on the x-axis and the number of Nobel Prize winners in the population of a certain country on the y-axis. And clearly you see there's a pretty strong correlation, and the p-value also tells us it's significant. And now I have 3 candidate graphs for you, and you should tell me which one you think is at least somewhat correct. So who of you thinks that chocolate causes Nobel Prize winners to rise? I hope no one. The same holds, of course, for the reverse direction. I don't think you are forced to eat chocolate once you won a Nobel Prize. And probably the correct graph would look like something like this, where we introduce 2 additional variables in this case, which we would call then confounders subsequently, but we will see that. Here we have the wealth of a country measured in some way. We have an educational level. We assume that we also can measure this in some way. And they influence, so the wealth influences the educational level, which in turn leads to more Nobel Prize winners, hopefully, you do it right. And also wealth is likely to influence the chocolate consumption somehow in a country. So following statistical relationships blindly isn't a good idea, because imagine you as a country ask yourself, okay, what can we do to get more Nobel Prize winners, to get smarter people? Yeah, then your conclusion shouldn't be, well, let's eat chocolate. Yeah, so that's why we need causal discovery. Yeah. So we already saw this slide, right? And that's just another example of how the graphical representation and the SCM definition kind of correspond to each other and how they react to interventions. Yeah, so in this we have this example here. Again, a simple graph, 3 variables in this case, 1 exogenous variable, and yeah, basically this causal structure right here. And due to this kind of, we have a push forward measure here, which yeah, leads to a distribution induced over all these variables. And I just do it quickly if that's okay. And for you, just here are the equations for some specific SCM, yeah, based on these variables. And if we intervene, in this case on x2, then this really leads to a completely different SCM definition, as we now fix this value of x2 here, which simply means that we cut off this certain edge here. So that's just for you to get, again, an intuition on how SCMs and Bayesian networks, for instance, or the graphical representation then differ. Okay, we've seen all this. What is causal discovery then? A very general definition reads as follows. So if we have an SCM with an associated causal graph, and we obtain some data from this SCM, then we aim to reconstruct this graph G, and we can say we have some kind of function that maps these data sets to its corresponding causal graph. And one important thing you should keep in mind is that we can possibly see multiple data sets from different distributions, because if we intervene, if we have the possibility to intervene on an SCM, we might see this leads to a different distribution, and we might see a different data set. So if you have 2 data sets and one telling us, oh, this happens if you intervene on some certain variable, then we can probably recover more of the causal structure as if we just would have observed a purely observational data set. Typically, you make 3 assumptions in causal discovery, which I have listed here. Let's go through them step by step. So the first one is the so-called Markov assumption, which intuitively states that all the deseparation statements in your graph translates directly to the joint distribution. So all the deseparation statements in the graph are encoded as independencies or conditional independencies in the joint distribution. And faithfulness is basically the other way around. So if you have conditional independencies in a distribution, you say you want them also to be in the causal graph, somehow encoded as deseparation statements. And the third assumption you usually make is causal sufficiency, which simply says that you observe all the relevant factors for your causal system that can be observed, so you don't have any hidden confounders. However, we will also have a brief overview over an algorithm that kind of weakens this assumption to some extent. But usually you make this assumption. So let's start with the first, yeah, the second section and the first family of causal discovery algorithms, which are named constraint-based causal discovery, as they employ certain constraints and use independency tests for recovering the structure. So the key idea is that we have the Markovian assumption and the faithfulness assumption, which yeah, imply a one-to-one correspondence between deseparation and independencies in the distribution. And we can exploit this because we can then reconstruct the graph with the correct deseparation statements. And the second key idea is that we can exploit the somewhat special behavior of the collider nodes to orient certain edges such that they are guaranteed to be the correct causal one, as long as our assumptions are met. And we will now look at the PC algorithm, which is already pretty old by now, but it's still a good way to get familiar with causal discovery. So let's go through an example. Yeah, so we assume that we have this this SCM here. This is our ground truth. and we observe data from that SCM. And the PC algorithm then goes ahead. I have just put this here for you. You don't have to read it for now in detail. What this algorithm is doing is it starts with a fully connected graph and tries to remove edges as long as possible. So we start with an empty conditioning set, which basically means that we condition on no variables. So we check for direct independencies in our variables. And this is our first step we do, which gives us this graph. So we remove two edges in this case, x5 to x1, x5 to x2. And now we increase the size of our conditioning set. Now we include one variable in our conditioning set, and we iterate over all possible variants of putting one variable in our conditioning set, which again gives us another graph, another reduction, so to say, which already represents the skeleton, at least, of our SCM as we have seen before. And now we can start and orient some edges. So for instance, we can identify this collider on x3. Why can we do this? Because if we save our independency test results, and we then can come back to them and basically see that if we would include x3 in the conditioning set, then suddenly x1 and x4 get dependent, and thus we know that x3 must be a collider. Yeah.
How do we know when we need to stop with the independence tests in the step before?
Well, if you don't find any independency anymore, then you can simply stop.
Okay, so at
because
every level, if you take one, then two variables.
Yeah, because you have this increasing set of conditionings. Yeah, in the conditioning set, you can show that you
as
can
soon
stop
as in one level we don't get any new ones, we can stop.
Yeah. Okay. Then there are certain rules that basically tell us how we can orient edges after we found the correct separation statement or the skeleton and V structures. And the first rule is pretty easy. It states if you encounter such a structure right here, and you have an undirected edge here, and you have a directed edge there, then on xi, in order to avoid a collider, you cannot turn the edge such that it points from xj to xi. So you have to orient the edge the other way around. Similarly, if you possibly, to be honest, I haven't seen a case where this really happened, but the second rule states if you have an edge, and this dashed edge should tell you we have both edges in our graph somehow. So we have the directed edge from xi to xk and vice versa. Then we have to break the cycle because it's a cycle, right? So you have a feedback loop there. We have to break the cycle, and we do it such that we cannot get a collider on xi because we already identified all the colliders, right? So we can infer that we have to move the edge, orient the edge such that it does not point to xi. Then there are two more rules considering more complex arrangements of variables. So in this case, we have a directed path from xu over xv to xj, and we now can infer that the edge between xi and xj must be oriented such that xi points to xj. And why is this the case? Simply because if we did it the other way around, then in order to avoid a collider on xi, we would also have to put this edge in the direction to xu, which in the end would induce a circle, which is a contradiction to our assumption. And similarly, the argument can be made for this kind of graph structure. So if we would would orient the edge such that it points from xj to xi, then we should have to avoid a collider here, and we would again get a cycle.
I'm sorry.
Yeah.
Why do we have to avoid the collider?
Because we already identified all the weak structures,
Oh.
and by assumption we cannot get any anymore. So we destroy the independency statement. However, PC comes with certain assumptions that might not hold in real life. So, for instance, hidden confounders. I've already talked a bit about them, and also selection biases. Yeah. Imagine, for example, the following scenario. Say you have a company selling product X. Maybe X is a coincidence, maybe not. And you suddenly realize that the users don't use your product as heavily as a year ago. So to find out why this is the case, you set up a questionnaire and you send it to users, and they can fill it out or they cannot do. So you don't have control, basically, whether they will fill it out or not. Afterwards, you aim to identify causal relationships between the answers, let's say, of the users and their behavior. However, you have at least two problems here. Yeah, you have two problems here. The first one is selection bias, because obviously, if you send out the questionnaire to all users, probably only the heavily active users will notice that at all, and maybe will fill it out. Some users don't have the time for that, and this already gives a bias in the data you collect, right? And also you have probably some hidden confounders you simply cannot measure. So, for example, I don't know, why didn't some user fill out a certain question or something like that? You have no control over that. So the assumptions of PC would already be violated. So there's an algorithm that kind of weakens this and to some extent allows for selection biases and hidden confounders. This one is called fast causal inference, and also it speeds up PC a little bit, but that's just a side note. So yeah, here again are the two reasons why the assumptions of PCs will probably fail. And what FCI is doing, essentially, it splits the set of variables into three subsets. So the observed ones, denoted by O, latent ones, which are hidden, you cannot see them, measure them, and selection variables, which are related to handling the selection bias, essentially. And FCI then gives you a so-called partial ancestral graph, so PAC for short, which either indicates causal connections identified by FCI among the observed variables, or it indicates that you have for sure a hidden confounder, or that you might have a hidden confounder. However, obviously you have to make some further assumptions, but we will not go over these in detail in this lecture. So as PC, FCI has a set of rules. I think it's, I don't know, 10 or 12 rules. So you could make a lecture out of FCI alone to orient edges. And it first also identifies a skeleton, so the encoding the independencies in the data. And then you try to orient rules. And what you get is a graph consisting of several types of edges, where regular directed edge, as we have seen it so far, means still A causes B. If you have such a circle on one end, but an arrowhead on the other end, you say that there's no set D-separating A and B, so there's definitely some kind of dependency. However, you know that all paths end in B. And you can also have the case where you don't know that all paths end in B, so they could end in A, they could end in B, but you don't know. You just know there's some kind of dependency. And this double-headed edge indicates that you definitely have some hidden confounding there. So a brief summary for constraint-based causal discovery. We have learned that CD, it's constraint-based CD, recovers the MAC of a causal graph, however, not the entire causal graph based on just observational data. FCI kind of allows for selection biases and hidden confounding under several additional assumptions. And one thing we haven't learned so far, but that's something you should also keep in mind. The runtime of these algorithms of both FCI and PCR, in worst case, exponential, which is horrible if it comes to larger problems. Okay, then let's have a slight paradigm shift now and then look at score-based causal discovery methods. They don't rely on a dependency test. Rather, they define a scoring function which evaluates your graph given some data, such that a graph that explaining the data better than another graph receives the higher score. And then you simply try to maximize the score. However, naively iterating over the set of all DAGs is not a really good idea. I think Matej already told you that the number of possible DAGs grows super exponentially in the number of variables you have. So you need a different approach. And many score-based or many algorithms in the score-based domain use a greedy approach. So what they do is they identify the best graph so far. They start at some point, and we will see that in a minute. They start with some graph, identify a neighboring graph, which is kind of explains the data better. And then based on this identified graph, you again produce a set of neighboring graphs, and you go that way along until you find some optimum. And as it is common for greedy algorithms, you obviously can get stuck in local optima. The scoring function used for, in this case, greedy equivalence search, which is one algorithm following that approach. But this scoring criterion is used pretty often, is the so-called Bayesian information criterion, which basically is a regularized version of maximum likelihood score in the end. So you have maximum likelihood, the log likelihood here, indicating how well your learned model fits the data, and then you have some kind of regularization favoring easy or simpler models. That's the idea. So for GES, greedy equivalence search, GES for short, we need some definitions and also some additional assumptions. We will just quickly go over them. So first of all, we need to know what a covered edge is, and a covered edge is if you have a graph G with an edge between xi and xj, then this edge is called covered if its parents set happens to be the parent set of the its parent union the variable itself. So for example, in this graph, the red edges are covered edges. If you look at x2 and look at the parent set of x2, it's x1, and this equation is fulfilled, right? Because the parent set of x1 is the empty set, there are no parents, and then if we take the union with x1 itself, we get the parent set of x2. And you can check this for all these edges marked in red here.
I think in the second lecture, we defined the parent set to include the variable itself. So just for reference here, it is without variable.
Yeah, exactly. So the parent set in this case is a small set, the set of nodes that have that come into your x2 in this case, but not x2 itself. Okay, then there's a important lemma that we should kind of keep in mind for GES to understand. So if you have a DAG and we have some covered edge within this graph G, then we can reverse this edge and still remain in the same Markov equivalence class. And we will see an example in a minute, I think. So the reason is, if an edge is covered, this implies that if there's a collider, this collider is shielded, which basically means that if you condition on this collider, you still have the same independency statements as if you would not condition on this collider. So this doesn't change anything. Well, we will see an example in a minute, I guess. Or no, let's get back. So in this case, here we would have a shielded collider, yeah, because x3 is a collider, obviously, but there's an edge between x1 and x2. So if you condition on x3, this edge, so this, if you remove this edge, then x1 and x2 would anyway get dependent. If you don't condition on x3, due to this edge, you still have this dependency, and thus you are still in the same Markov equivalence class if you turn around one of these covered edges. Based on this lemma, you can then go ahead and define the so-called Chickering sequence. I hope I pronounced this name correctly, which basically tells you if you have two graphs where H is an independency map of G, which simply means that that H entails all the independency statements of G, but G might entail more of them. Then you find a sequence of covered edge reversals or edge additions, such that you find a path over DAX, such that your starting DAC is G, and your end DAC is H. So you can turn G into H by adding edges or reversing covered edges. And the intuition is, as we have seen, if you reverse a covered edge, then this holds in the same Markov equivalence class. And if you add an edge, this means you basically remove an independency statement, so conditional independency, for instance, which, if you look at this relation here, tells you pick out one of the independencies in this set of independencies. So this set gets smaller, and thus you get closer to the dependency set of H, and eventually you will end up with H. Okay, two more assumptions, and then we will see an example. These two assumptions are just to ensure that your score is making sense in this context. So the first is decompositionality, which basically states that you can compute the score as a sum of local scores. If you consider a certain variable, you can compute the score of this variable in terms of its parents. And if you do this for each variable and you sum these values up, then this is your global score for the graph. This is just to ensure efficient computation. And consistency, which just tells you if a graph that is closer in terms of encoding independency properties of a distribution as another graph, then the graph that is closer to the independencies in the data should be rated better. And if both graphs are working equally well in that regard, then you favor the simpler model. All right, let's step through an example. So we have, again, a ground truth, which looks like this. And GES now would start with an empty graph. And as we have seen, starting with a graph with a superset of independency statements, then some graph we want to obtain, then we can probably get there if we either reverse covered edges or we add edges. Since we don't have any edge here, we just add an edge, and we do it such that we iterate over all possibilities in this case and identify the edge that yields the highest score, and that's the greedy part of this algorithm. And we can then add another edge, and you see this edge changed. So this was reversed because it's a covered edge. We can do that. And we add an edge from x1 to x2 to x3. And we keep doing this. We keep adding edges. And at some point, we stop. And I see that there's still a mistake on the slides because there's an edge missing. But anyway, let's proceed. So after you have identified after you have reached a local optima or some kind of optimum, then GES stops and starts a second phase, which basically does the same, just backwards. So it eventually it might remove edges again, or it will reverse covered edges. The reason why you have to do this is in the forward phase, it might be that you find a graph which is over-parameterized in a sense. And this backward phase can bring you down to a more simpler model that explains the data still equally good or maybe even better. And in this backward phase, you can, again, reverse covered edges or remove edges. And then we end up here and imagine there should be another edge. Forgot that. Okay, let's have a brief summary on score-based causal discovery. So we've seen that you have to use either greedy algorithm or make many assumptions in order to get your problem feasible, as the number of decks in the search space climbs super exponentially in the number of variables involved. Then you have some scoring function that evaluates the quality of your graphs. You have, again, some assumptions on that scoring function, decompositionality and consistency. And as you are greedy, you can get stuck in local optima, so you cannot really guarantee to find the optimal graph. And as with constraint-based causal discovery methods, if it comes to very large problems, then this gets slow. However, there are also parallel implementations of GES that can try to make it a bit faster, but yeah, parallelization you can at max get a linear decrease in runtime. So if this is if this grows larger, faster than linear, then you're screwed up anyway at some point. Okay, then let's go to the last section. By the way, how much time do we have? Yeah. Okay. Yeah. All right. So I have told you, and you have seen it by now, with the score-based and constraint-based causal discovery methods, we can only recover the causal graph up to Markov equivalence. So at the same time, we were pretty general. Yeah, we didn't make any assumptions regarding the distributions of the variables. And we didn't even make assumptions on the functional form, so they could be linear, nonlinear, whatever. As long as we have an dependency test or a scoring function that can kind of handle that, we are fine. However, what if we have some assumptions on the distributions, on the functional form? Can we do better than Mac? Turns out, yeah, we can. And we will see yeah, I don't want to call it easy example because it's could be a little bit confusing in the beginning, but I hope you will manage. So if we look at a bivariate case, then we have the following lemma, which tells us that if we assume non-Gaussian distributions as noise, then if we have consider two models, like one forward model, which reads y equals ax plus n, and a kind of backward model, which reads x equals by n prime, which is just a noise term. And if the noise is non-Gaussian, then you can show that based on observational data, you can indeed identify the correct model. So whether it's x depending on b or y caused. So whether it's x caused by y or y caused by x. And this little example is supposed to visualize this to some extent. So in the upper left corner, we have a Gaussian case, or in the upper on the upper example is a Gaussian case, and the bottom example is a non-Gaussian case. And on the left-hand side, we have a model fit from x to y, and a model fit again from x to y, and we assume that the correct model is indeed x to y. And as you can see in the Gaussian case, you can also fit a model y to x, and this graph here shows you the residuals and the covariates. So in this case it's x, and in this case it's y, and you see that in both cases the variables are independent of each other. However, if you look down here, you find that the residual variable and the covariate variable is independent if you fit in the correct direction. However, if you fit the model in the wrong direction, you find that there's a dependency suddenly, and you can prove that this really holds for as long as you have linear dependencies, so linear functions. You can prove that this is the case for any linear system, basically. So a simple algorithm in this case to identify the correct causal order would be, for bivariate cases, you should keep that in mind, fit a model in both directions and kind of save the residual somehow. And then for each direction, you can just test using some independency tests like HSIT you already know, I guess. So it's similar to what you would use in PC, for instance. You can then simply test whether the residuals are independent of the covariates or not. And once you found the direction for which the dependency holds, then you simply can say, well, yeah, that's the correct causal direction. However, there's one thing that you should also keep in mind here. If you do this fitting, you should use a non-parametric model, because if you use a model with Gaussian noise assumptions, which is pretty common with linear models, right, then this is most likely a bad idea, because yeah, you have this assumption, and I think this wouldn't work then anymore. Can we extend this from bivariate cases to n-variate cases? Turns out, yes, we can. And we now will have a look at two algorithms that perform pretty similar things, but in a different way. So the first one is called RESIT, and the idea is that we can exploit the fact that each noise variable of some variable in your graph is independent of all the non-descendants of xi. Yeah. So this means simply that if you have some variable in your graph and you go down the path, if you go down follow the causal path, then you will have a dependency to this noise, obviously because it kind of contributes to xi, right? But all the variables that are non-descendants, they are independent. And then you can go ahead and follow a two-phase algorithm, to identify the causal graph. So first of all, you construct a topological order of the sync nodes. So you start with a set of nodes which is all nodes in the beginning, and then you select some node and exclude it from and regress this regress all remaining variables except the one you've just chosen on the X you've chosen. And you do this for all the combinations, and you simply choose a sync node based on the level of independency-ness, if you want to put it like that. So the combination that maximizes independency between the chosen variable and its parents is then deemed to be a sync node. And you do this until your set of nodes S is empty. So you have then this topological order. And in the second phase, you can traverse along this topological order. And we are guaranteed to have such an order because we have acyclicity still assumed, right? And we then can try to remove edges that are not needed. So kind of try to find a minimal model that still explains our data, and we just proceed in a similar way. We regress each sync node X on its parents, and we keep removing variables from this parent set until we find that this independency statement does not hold anymore. The intuition behind this is that, again, if we have the dependency between covariates and the residuals, we have identified the correct causal direction. And since we are in varied cases now, we try to maximize these independencies along the topological order. This is the algorithms just for you in case you're interested in the details, but we won't go over that now. Another method that follows a similar idea is called lingam. And again, you assume linear dependencies and non-Gaussian noise, and you exploit a method from statistics called independent component analysis, which we will have a brief look at in a second. But the key idea is that ICA, which makes similar assumptions as we now have, so non-Gaussian noise, linear dependencies, and ICA tries to solve the following problem. So if you have given some data which originates from a linear mixing mechanism, so assume you have S, which is a vector of independent components or a matrix of independent components, and you try to obtain A, which led to the data X. So it's a bit like this cocktail party problem. Maybe some of you know that. Yeah, you have multiple persons in one room, and you cannot really listen to all of them, right? You have to focus, but what you get is a mixture basically of signals. And what you want to try to do is to revert this process, find the unmixing matrix basically, or the mixing matrix by inversing this process, such that you can reconstruct the independent signals again. And it can be shown that ICA recovers this matrix up to scaling and permutation. So we are not done yet with the ICA. Just applying ICA won't give us any causal graph, unfortunately. But we will see we can. We only have to permute a little bit, and we don't really care about scaling when identifying just the graph structure. So if we can permute the matrix correctly, then we have a causal discovery algorithm. So let's dive a bit more into the details as we have still some time. So we assume linear SCMs. We have, again, this independent noise, the independent noise variables. We have a matrix describing how the variables are connected with each other. And this is simply a matrix formulation of this and we will see an example an example on the next slide. And we can also say that B represents a DAG. In this case, this would just be a weighted adjacency matrix, and this allows us to write the data, so X, in terms, or our variables X, only in terms of noise variables. And it happens to be the case if we set A to be the identity matrix minus our matrix B, which defines the causal structure in a sense, inverted. And we can see this on using an example. So we have this SCM here, as usual. Yeah, so we have 3 variables in this case. As you can see, everything is linear, our linearity assumption. The matrix form, we can write it like that. And now consider X3. And as we have like a chain basically from X1 over X2 to X3, you can try to write X3 in terms only of the noise variables. So go ahead and write down the definition of X3, and you can keep going and replace the definition in this case of X2 then with the definition of X2, and you can recursively do that until you end up with that one, which, as you can see, only contains noise terms. Yeah, and the intuition why this inverse of this matrix comes into place, that if you write a variable only in terms of its noise variables, then it's similar. You can think of it as skipping the intermediate variables. However, you have to account for this, obviously, yeah, because as you walk down this path, you kind of accumulate the factors that describe the dependencies in these intermediate nodes. So your matrix has to capture this somehow. And if you write this only in terms of noise, you end up with this matrix A in this case. And if you do the matrix multiplication of the A, so this is then this inverse here, and the correct order, so the B we started with, then you see, if you do the math, you see that you end up with the identity matrix, which is a pretty complicated way of saying A should, multiplying A with the noise should be exactly the same as going down this recursive structure. Maybe if you look at that a bit more detailed, if it's not clear, then I'm sure you will see it. So back on that slide, we have now seen that this really holds, and we maybe hopefully have some kind of intuition on that. So now we are sure that we can really see this as an ICA problem and use ICA to solve our unmixing problem. And ICA, just very briefly, what ICA is doing is, as I said, you have two independent signals. Yeah, in this case, these are our noise variables, and you have some mixing matrix A, which in our case would represent the SCM, which mixes these signals. In this case, you kind of rotate this base in here, right? And what ICA is now doing is to undo this rotation, basically. And the central limit theorem tells us if we keep adding up random variables, the mixture will be more Gaussian than the components. So what ICA is doing is it minimizes Gaussianity of the independent noise terms. And by minimizing that, you can find the inverse process, which gives you this matrix in the end, and you end up with the independent signals again. Below there's an example of Gaussian distributions, and as Gaussian distributions are kind of circular, so to say. If you look at that, right, it's two-dimensional in this case, like a circle. And if you rotate a circle, well, yeah, good luck finding the inverse. So that kind of gives an intuition why this doesn't work with Gaussian noise distributions. So once you have this A obtained, then you just compute the inverse of this, because remember that our A is defined like that, and we are interested in B. However, W is not the solution yet. Did I say B? I don't know. So what's missing still? ICA doesn't really. So ICA gives us a random order with respect to the noise term. So it doesn't really care about the correspondence of the noise terms and how we mix them up, so to say. So we have to permute the rows of the matrix still. And we can do that by saying that, and I have a slide on that, by making the diagonal of the matrix non-zero. And after we have done this, as we have a directed acyclic graph assumption, we can then make the matrix we obtained from step one. We can make it lower triangular because it's a DAG, which then gives us the correct causal graph. So looking at the first problem, just intuitively, we have to find a permutation such that the diagonal is non-zero, which intuitively makes sense because remember the definition of this of A, which was like I, so the identity matrix minus B inverse, right? And you have due to the identity matrix, you have the diagonal filled with ones. These ones kind of ensure that you can represent this whole system in terms of the noise variables only. So making the diagonal non-zero makes sense, right? And once we have done this, and we can do this with some kind of optimization algorithm, we have to optimize this because as we are working with samples, there might be some noise. So we cannot assume that the diagonal entries are really zero. So we have to optimize this. And finally, if we have done this, we have to find another permutation that makes the matrix lower triangular, and we are done. I know this was a bit heavy now, but I hope that you've kind of got the intuition based on the visualizations. So it's really about making things independent and kind of reverting in the mixing process. And this permutation stuff, I mean, you can show it, but I think for this lecture, it's enough to kind of know that you have to do it. As a brief summary, with non-Gaussian noise assumed, we can recover the full causal structure given only observational data, which is great. Underlying reason is that, as we have seen, if we fit a model in the wrong direction, we find that the residuals and the covariates get dependent. So we have to ensure that they are independent, as we assume independent noise, right? And again, we can get stuck in local optima, as also ICA is also non-convex optimization problems. And one thing we did not look at was nonlinear dependencies among variables, but there are also methods looking at that. Sometimes it even turns out that even Gaussian noise is then no problem anymore. But I think for today, it's enough if we have looked at linear system. Yeah.
Aren't noise, real-world noise signals are Gaussian?
That's interesting. I mean, intuitively, this makes sense due to central limit theorem. Yeah, you have multiple factors that you cannot observe, and they tend to be Gaussian in the end. but they're the authors of, I think, Lingam. I don't know if it was Lingam. They have analyzed this to some extent, and they indeed found that in many, especially in social sciences, it is not the case. It's more frequent to have non-Gaussian noise, which I found surprising as well. But yeah.
I think one argument was, like Christian said, I think in the first or second lecture, as soon as you have distributions which only look at like positive values and so on, right, where you cut away some of your domain, you can't have a Gaussian distribution, right? Because at some point you cut off the distribution, so it's non-Gaussian anymore. So it happens quite often.
Yeah. Yeah.
So is it right that with that we can just use, we have a data set and with our assumption that we have non-Gaussian noise, we can now find any, like, all the dependencies?
I mean, you have also the assumption that you have causal sufficiency, right? You don't, if you have a hidden confounder here, this wouldn't work reliably anymore. So as long as you have causal sufficiency fulfilled, yes, but this is rarely the case in real world. Yeah.
I'm also a bit confused as to why these algorithms even uncover causal structures. Like, I expected some talk about interventions or counterfactuals. Like, where does this happen? This has to happen somewhere, right? In the algorithm. Like, so that we even know that there's like a causal effect and not just an observational correlation.
Yeah. Okay. So you mean you're surprised in terms that you would have expected that if it comes to causal discovery, you would have to intervene somehow.
Yeah, somehow.
Yeah. And that's totally makes sense. Sure. And there are also methods that assume access to interventional distributions. And you can show that as soon as you have access to such distributions, you can recover more of the causal structure. However, imagine in the real world, if you're a social scientist, right? You oftentimes simply cannot intervene. I mean, societies are growing as they grow. You cannot really control this. And sure, you can try to have a controlled environment, but most of the time you cannot have such an environment. It's too costly. It's impossible. So you need these methods to also get something out of observational data only. That's the reason why these methods exist.
Manage causal dependencies if they don't use interventions or counterfactors. Like, there has to be some mechanism, right?
Assumptions.
Okay.
Assumption is the key word here. In case of ICA and so these additive noise models, you have oftentimes the linearity assumption and this non-Gaussian noise. And as you've seen, then to some extent we can recover causal structures. But the former two ways of doing causal discovery, you have seen that we only can recover the MEC, so the Markov equivalence class. And this, in the end, really just shows you dependencies in a sense, plus these restructures and following the rules, some more identifications. But again, you have a cyclicity assumption, which might not hold in real world. You have the assumption of causal sufficiency, that you really observe everything you have to observe to recover the causal structure, and some more assumptions, macroeconomic faithfulness, and then you can manage to get something out. But okay, yeah, you cannot really test whether these assumptions really hold, or it's hard to test at least, sorry, I will come to you in a second.
Some basic question on notation. So with this noise notation, you simply just combine all exogenous variables per endogenous variable to label it with some noise value. So then not talk about use, just have one noise term or noise random variable per endogenous variable. Because at some point you switch to n and
true. So sorry, I should have mentioned this. So this e is the same as the n right here. It's just noise.
Okay, and e they are just exogenous variables.
Yeah.
The second question regarding the assumption of non-Gaussian noise. So what happens if you have in fact Gaussian noise on a data or in a data set, but assume non-Gaussian noise and run these algorithms?
Well, you screw up, it won't work. Your assumption isn't met, right? If you have Gaussian noise and you assume non-Gaussian noise,
what's the result? So
maybe you get some dependencies, but you cannot really interpret them as causal.
So edges are randomly flipped, for example, and these kinds of stuff.
But I'm not sure whether there are any guarantees on that. I just know that you are allowed to have at most one Gaussian variable, then this still works. But yeah, as soon as you have more, I would agree. Then you probably have just randomly flipped edges. Yeah, we go that way. So I think you also wanted to ask something. Okay, then your neighbor.
Okay.
Or yeah.
I have one question regarding why Gaussian experiments don't work. So in the pictures you showed, it seemed like it doesn't work because you cannot say which way it was transformed because it seems the same. There are other distributions that are where you don't see the transformation, right? Or is
so you mean other distributions than Gaussian where you have the same
or is this only Gaussian? Because it seems so strange that it's only one specific distribution and not
the thing is, so according to the authors, it's non-Gaussian. But I agree, as soon as you have some distribution that is kind of circular, then you would face the same problem. Are you aware of another distribution with this?
But it's not the whole exponential class.
It's not the whole exponential class, no. But so I would agree intuitively if you have some circular stuff going on here, then you cannot identify. But imagine if you have, let's say, if you skew this a bit, right, then you don't have a perfect circle anymore. Then you might have a chance again to But yeah, intuitively, I would agree. Yeah. I think you had a question.
First of all, regarding Gaussian models, I think Gaussians are very naturally in nature. You're repeating the theorem and repeating the same kind of measurement. You're always observing Gaussians. As soon as you're not observing Gaussians, there has to be some kind of influence on the measurement. I guess. So maybe this could be the case because we can extract some causal relationship between variables where the noise is not Gaussian. Could be. Is it just an assumption?
Can you repeat?
So Gaussians occur pretty naturally.
Yeah.
The same measurement over and over again. You can expect to be the error to be Gaussian. And as soon as the error is not Gaussian, you either have lost because you cannot quantify it. Or you can assume that you have a causal effect onto a variable that has a non-Gaussian value. And that might be an indicator for there might be causal bridge. Might be just an assumption. But I had another question. So I assume that you have two different processes. The first process, you use observation data to extract the causal relationship and make the dependency discoveries, the graph discoveries. And then in another experiment, you use that graph to enhance the prediction algorithm. And my question is, can you try to extract the causal graph from observation data and use the same graph with the same data to enhance predictions? Does it make a difference in compared to just observation studies?
So you have observational data, you extract the graph, and then you use the graph to influence your experiment process.
Yeah, but make predictions of the same data you already use to extract the graph. So could that bring any improvement to predictions just based on observation?
So you want to have a feedback loop, basically.
But you're doing causal inference and observation field on the same time. And that's not exactly what I mean. It's in the standard scenario, do you use this discoveries and the graphs you're extracting, the same experiment to improve predictions based on the experiment, or one experiment, or you have like one experiment they extract the graph, and another scenario with new data they try to make it.
So the way I understand your question is whether, or the way I interpret your question is, if I identify a causal graph and use the causal graph to make predictions that influence the data generating process I just have discovered, whether this is still kind of a useful model because my decision might influence the causal structure again, right? Is this what you mean?
Basically, I'm just wondering, you always said, like, if you have a causal graph,
yeah,
and this can improve our predictions compared to just having observation.
Yeah.
And could be like, do this hack where we use observation data, recover some graph structure, and then we say, okay, we have our intervention model, or a model, and now can like do better predictions, although we only have observation data. Like, does that make sense? Can be like,
yeah, there are actually approaches I think that have a the same idea. They define different environments where you observe observational data, but you don't really know much about these environments. So you don't know are there interventions being performed or so. And then you can indeed show that having such environments can indeed help identifying more of the causal structure. I think that goes in the same direction somehow. So I would agree, yeah.
I understand this question something like, is there any benefits from retrieving such causal graph in describing some situation or learning about some situation? Because if you think about, there's some causal knowledge in this form of observational data, you can come up with a different technique to extract the causal information out of the data. So is there alternative for extracting this causal data, or some maybe not as identified as causal discovery method that is used somehow with non-Gaussian noise data that is commonly used, and now we have this causal discovery and we can compare the predictions or something like that.
I'm not quite sure if I get it.
So maybe is this in some sense groundbreaking, for example, in fields where they have non-Gaussian noise, or have they had their own method of extracting causal information of observational data? Because with the same assumption, there's somehow a proof that it's possible. So there might be another method they used in the past.
I mean, sure, they might be. I mean, we have seen two methods today, right? Sure, there might be other ways to do it. But I think you still have to rely on a certain set of assumptions. So, I mean, sure, you can go ahead and weaken maybe the linearity assumption and allow for certain non-linearities. But yeah, the assumptions are the important thing here. That's
so. Do not know of any methods that are currently used or were used in, I don't know, or other humanities that build models and think about these things without causal discovery.
Yeah, I mean, but then again, if you don't have this notion of cause and effects, then I mean you end up with correlations again, right? I mean, sure, you might be able to induce some kind of order in a sense,
But
Or
that's the
you-
question, is if the observational data allows for causal discovery in this sense, maybe it also allows for causal discovery in more traditional sense, because some observation, I don't know, maybe there's some other technique, or there were no technique, and this is more kind of proving that it's doable in the first place, or that's
to the best of my knowledge in terms of causal discovery, at least in this Pernian framework, this was one of the first doing this non-Gaussianity assumption. And I mean, ICA itself isn't that old, I think somewhat in the 90s or so. So yeah, I think that in terms of causal discovery, as we have seen it here, it's one of the first really successful methods of doing so. Yeah. All right. Sorry.
My question is just like, how useful are those models if you always have the risk of having some confounding variable that didn't model?
That's case dependent. I mean, in some cases, you might know that your environment is somewhat controllable, or because you have domain knowledge, you know that there are certain factors that you encounter in later. But you cannot really tell this in general. But I mean, if you use it, always keep in mind that these assumptions are there and they are not guaranteed to hold in reality. I would say they are useful to some extent, and you might also be able to at least get a rough estimation then of causal effects if you then use these models. But I wouldn't guarantee that this is then really kind of exact or unbiased or whatever. All right. Then that's it for today. Yeah. I don't know if I can say see you next week. I'm not sure whether I'll be here, but yeah, enjoy next week's lecture again.